All right, welcome back to another calculus lecture. So in today's lecture, what I want to talk about is a sort of extension of the idea that the integral is, it represents the area underneath the curve, or between the curve and the x-axis. So the scenario that I'm interested in is actually when we have two curves, and I want to look at the area between those two curves. So suppose that I have two functions, f of x and g of x, such that f of x is less than or equal to g of x for all x in some interval a to b. Then we would like, I don't know why I put a comma there, we would like to compute the area between these two curves, between the graphs of f of x and g of x. So I could have something like, if I get my ruler out, draw a quick graph here, something like this. So here I have f of x and g of x. I don't know. Doesn't have to be anything specific. But here's A, here's B. And then what I'm interested in is actually just computing this shaded area right here. So this is g of x, f of x. So for g of x to be greater than f of x, it just means that its graph is above f of x. So I'm interested in how to compute this shaded area right here. Well, if I sort of think about doing this with integrals, then what am I actually going to compute? Well, I know that the integral from a to b of g of x dx, this is the area below the graph of g of x. At least in this specific case, the integral doesn't always exactly represent this. We've seen cases where this represents sort of a net change. It's the sum of the areas between the graph and the axis. Some of those areas may be negative. But in this case, when g of x is positive, then this integral is certainly true. And likewise, I have that the integral of f of x dx is the same thing for f of x. And so if I'm interested in computing this area, this black area here, well, notice that if I just took the area for g of x, which is just, we'll do this in blue, this would be the area for g of x. It's just all of this underneath the graph, including this bottom part down here. Well, if I wanted to do this for f of x as well, then I can shade that part in too. And notice what the black area is. The black area is just the difference between these two things. So the area here is just the blue area minus the green area. And so if I want to compute this area, then I can just subtract the two areas. And so the integral from a to b of g of x dx minus the integral from a to b of f of x dx, well, the integral is linear, so I can actually just write this together. This is the integral of g of x minus f of x d of x. This will equal the area that I'm interested in. This is the area between the graphs of f of x and g of x. Okay, so if I'm interested in computing an area between two graphs, then really it's just the same problem as computing with integrals, except that I have to do this extra step of subtraction. And we'll see a couple of examples where you have to do a little bit more work, where the lines sort of intersect and you need to sort of switch your point of view. Okay, so let's, with this in mind, let's go ahead and just do some calculations for computing areas between graphs. All right, so example. So let's compute the area between the graphs of f of x equals, and it's going to be this polynomial, x squared minus 4x plus 10, and g of x, which is going to be negative x squared plus 4x. Okay, so I have these two functions, and if at all possible, it's always really helpful to draw a picture. So I've got this already, I've looked at the picture already, so we'll go ahead and just recreate it here. But you could certainly do this on a graphing calculator or something, you know, like Wolfram Alpha or Mathematica or some software like this. But the graphs are going to look something like this. So 1, 2, 3, and then we'll scale the vertical axis slightly differently. And, oh, and I should say between 1 and 3. So on the interval 1 to 3. So if I draw the graphs here, the graph of g of x is going to be a parabola whose vertex is at 2, 4, and it's going to sort of curve down like this because it's a upside down parabola. The coefficient of x squared is negative. And then the graph of f of x is going to be similar, except its vertex is going to be at 2, 6, and it's going to be facing, it's going to be opening upwards. And what I'm interested in is this area here. Okay? So, how do we do this? Well, we've sort of already seen that we can compute this area by computing a certain integral. So here we have f of x greater than g of x. It's the reverse of the notation I had before. When I was explaining this on the previous page, g of x was the bigger function, but now f of x is. Doesn't really make any difference, but we can certainly compute this area in the same way. So if I want this area, then I just do an integral. So this is going to be the integral. My interval here is 1 to 3. And then I do f of x minus g of x, the top function, minus the bottom function. And we'll go ahead and just put in what that is. So this is the integral from 1 to 3. F of x is x squared minus 4x plus 10. And then minus, and we'll put this in parentheses because we have to distribute the negative sign, negative x squared plus 4x dx. And now we try and simplify this because that'll make computing the antiderivatives a little bit easier. So I have x squared minus a negative x squared, so that's a plus x squared, so I get 2x squared, and then minus 4x, and then I have another minus 4x here, so this is going to be minus 8x, and then plus 10 dx. And now all I do is apply the power rule. So this is going to be, when I compute my antiderivatives, I have x squared, that becomes x cubed, and then I divide by my new exponent. So this is going to be, from this 2/3 x cubed. X here turns into x squared, and then I divide by the new exponent. So 8 divided by 2 is going to be 4, so 4x squared. And then 10 turns into 10x, because the antiderivative of 1 is just x. And I'm going to evaluate this on 1 to 3. Okay, so this is going to be 2/3 times 3 cubed minus 4 times 3 squared. plus 10 times 3 minus, and I like to use parentheses pretty generously just to make sure I don't miss distributing a negative sign anywhere. 2/3 times 1 cubed minus 4 times 1 squared plus 10 times 1. And if you put this in a calculator, we don't have to go through this computation, in any more detail than this. You can just put this in a calculator. This is going to give you 16/3. And so the area between these two curves, between the x values 1 and 3, is 16 divided by 3 units. It's like 5.3 repeating. Okay. So this is how we can compute the area between two curves. So let's go ahead and see another example, which is a little bit more complicated, where we're going to have to think a little bit harder. So example. So compute the area between the graphs of f of x equal to x squared minus 2x minus 6 and g of x equals x minus 2 on the interval -2 to 4. Okay, so again, it's very helpful to draw a picture, and if you want to see a picture, you can actually look at the supplemental notes. This is lecture 24 there. They're drawn much better than I'm drawing them here, but I just wanted to have everything in one video. So this is going to be 2, 4, -2, -4, -6, -8, and then 1, 2, 3, 4, 1, 2. Okay, and the graph of this, so we can actually think about what one of these graphs looks like. X minus 2 is just the graph of x, and then I shift it down by 2 units. So the slope is 1, and the y-intercept is -2. So I'm going to do something like this, and then it's just a straight line. And then the other of these graphs, if I sort of graph this, or I think about the vertex of this and solve for that, then the vertex is going to be down at 1 and -7. So like this, and then the graph is going to look roughly like this. And the area that I'm interested in is actually this portion. I've sort of drawn this incorrectly. Should be something like that. This portion and then this portion. So that's the area between these two graphs. So I actually have one function being the parabola is above the line for this section over here, and then the line is above the parabola for this section over here. So I'm going to need to do 2 separate integrals. So we need 2 different integrals for each section. So let's go ahead and think about what those will be. Well, we need to know where these points intersect. So we need to know where the graphs intersect. So let's go ahead and compute that first. Well, how do I figure out where 2 graphs intersect? I just set the 2 functions equal to one another and solve for x. So we do x squared minus 2x minus 6 is equal to x minus 2. And then we need to solve for x. So if we do this, let's go ahead and subtract x and then add 2. So this will be x squared minus 3x minus 4 is equal to 0. And then this polynomial I can actually factor. So this is, I think, about two numbers whose product is negative 4 and whose sum is negative 3. So that's going to be negative 4 and positive 1. So the graphs, the solutions of this equation are x equals 4 and x equals negative 1. So the graphs intersect at x equals 4 and x equals negative 1. So these are the points where I'm going to need to split my integral. So one of those points is actually the endpoint of the interval that I'm interested in, so I don't really have to worry about that one too much. But the other one I need to make sure I handle properly. So the area is going to be equal to, and now we just need to write down the two integrals. So the first integral from negative 2 to negative 1 is, I have the parabola above the line, so I need to subtract the line from the parabola. So the integral from negative 2 to negative 1 of the top function, x squared minus 2x minus 6 dx, and then I need to add the integral for the other section. So this integral is just the remaining section from negative 1 to positive 4, and now the line is above the parabola. So I need to do x minus 2 minus, and actually I didn't actually write down the minus x minus 2 right here. X minus 2 minus x squared minus 2x minus 6. That was the word minus quite a lot. Okay, so I've got these two functions. Now let's go, or these two integrals, let's go ahead and try and compute them, or at least simplify them to the point that we could compute them. Really, the main meat of these problems is setting up the integrals properly. Once you have those, it's fairly straightforward to apply the fundamental theorem of calculus and actually get a numerical value for these integrals. But let's go ahead and just do this. So this is negative 2 to negative 1. I have x squared minus 2x minus x, so I'm going to have a minus 3x, and then minus 6, these two negatives become a positive, so plus 2, so I have minus 4 dx, and then plus the integral from negative 1 to 4. And when you have the difference of two things and you reverse the order of the difference, all that happens is you actually just pick up a negative sign. So we're going to have negative x squared minus 3x minus 4. And if you don't believe me, you can sort of write this down and simplify and see that that is indeed what you get. Okay? So once we have these two integrals, well, we just apply the power rule. And in fact, it's going to be the same, pretty much the same power rule for each of these. But we can actually just sort of abbreviate this step because, you know, at this point, hopefully you can do this confidently, but I'll just tell you what the answer is. If you want to see the full worked out computation of this, you can go look at the supplemental notes. But the full computation is not really the point of this. It's setting up the problem that I want us to be able to do. But the actual answer is 125 over 6. So you can write down the fundamental theorem of calculus computation and apply the power rule and do all this, and this should be the answer that you get out at the end. And actually, it's not this. That's one of these integrals. It's the second one. The total integral is actually 71/3. So this first integral is 17 over 6, and the second one is 125 over 6. Misread my notes. Okay, so that is how you can do this integral computation where you have multiple sort of sections that you need to look at, where which function is on top actually changes somewhere in the interval that you are interested in. Okay? Now there is one more example that I want to work through, and this is going to be an example of a kind of integral where it's actually more sort of convenient to integrate with respect to y instead of with respect to x. So let me go ahead and write this down, and then we'll sort of talk through how to do it. So let's compute the area bounded by the curves y equals the natural log of x, y equals e, and x equals 1. So we need to, y equals 1, not e. So let's go ahead and try and get a picture of this. So here's my axis. So here's 1, 2, 3. And I'm actually going to have this be 1/2, just so this is a little bit easier to look at. So the graph, let's go ahead and just put in each of these lines. Well, these two are fairly easy. The graph y equals 1 is just this line, this horizontal line at 1. Same thing with x, it's just a vertical line. And then I need to think about what the graph of natural log of x looks like. Well, we know that if I take the natural log of 1, I get 0. And then if I take the natural log of e, I get 1. And so the graph looks something like this. This is y equals the natural log of x. And the area I'm interested in is this guy right here. Okay, so if I just go ahead and write down the integral that I'm interested in, well, I know that the interval over which I'm integrating is 1 to, this is like e right here. I'm going to integrate from 1 to e because that's where all these things intersect. And then I'm going to have the top function, which is just 1 minus the natural log of x. So my area is equal to the integral from 1 to e of 1 minus the natural log of x dx. And we sort of run into a problem because I don't actually know how to compute the antiderivative of the natural log of x. In Calc 2 you learn how to actually compute this, but for now we don't quite know how to do that. Well, we can sort of think creatively and say, okay, well, instead of integrating from left to right along the x-axis, why don't we actually just integrate from bottom to top along the y-axis? And we can certainly do this. And in order to do this, we need to convert our functions of x into functions of y. So these two just sort of say the same, but if y equals the natural log of x, then let's solve this for x. So if y equals natural log of x, well, I can just exponentiate each side, put each in the exponent of e to undo the natural logarithm, and we see that x is e to the power of y. And if I sort of turn the graph sideways, then if you were to flip this along the x-axis, you would sort of see that the graph really is just the graph of e to the y here, or e to the, it would look like the graph of e to the x. So how do we actually compute this now? Well, now we need to view this as an integral from the bottom to the top. So now my interval over which I'm integrating is going to be along the y-axis. So the area is going to be, now instead of going from 1 to e, I go from 0 to 1. And I have my top function now is now the right function, and the bottom function becomes the left function. So the left function here is the line y equals 1, or x equals 1, and the top function is the line x equals e to the y. So I just do e to the y minus 1, and now I'm going to integrate with respect to y. Okay? So hopefully it's clear what we've done here. Instead of integrating from left to right and looking at top and bottom functions, instead now what I'm going to do is integrate from bottom to top and look at left and right functions. So my left function being the line x equals 1, and my right function being the curve x equals e to the y. Notice now, this is an integral I can compute. This is just, well, taking antiderivatives, this is e to the y minus y, and then I evaluate that from y equals 0 to y equals 1. And this is going to give me e minus 1 minus e to the 0 minus 0. And this is, well, e minus 1, and then e to the 0 is also 1, so I have another minus 1. So this is just e minus 2, which is like 0.7 something or other. Not exactly important what the exact value of that is. The point of this is that sometimes it is more convenient in these problems to actually integrate with respect to y and look at inverse functions rather than just trying to integrate with respect to x. And when we get to solids of revolution, which is going to be the last thing we cover in this course, we're going to see something similar happening there, where it's sometimes more convenient to shift our viewpoint geometrically and make the analytical calculation more simple. Okay? So that's everything for this video. In the next video, we will talk about another application of the integral and look at some more things there. All right, so see you all in the next lecture.